this is what we're asking you to do. So Stephen's question is question 1, mine is question 2. There's 50 marks going for each, so that's half and half on each of the 2 questions. So my question is all about using partial differentiation to do various things. So the first part, there's 4 parts, A, B, C, D. The first part is an application of the small increments formula. Okay. Now this is centered on this function x to the power y. Okay. A function of 2 variables, x and y. And well, if we look to part 2 of question A, it's all going for this quantity here. So this quantity, 1.97 to the power of 2.01. If you type that into your calculator or type it into Matlab, it spits out the answer for you. But to get a bit of a clue about how it might, some of the basic principles about how the computers can obtain values for these kind of things. Question A kind of brings you through finding a first order or a linear approximation to this value based on the nearby value of, where if you evaluate the function f at x equals 2 and y equals 2, then you're just talking about 2 squared, which of course is 4. Just from basic arithmetic, no fancy computation needed. 2 to the power 2 is 4. We know that. This is a value close to that. Okay, something close to 2 raised to the power of something close to 2. So its value is going to be close to 4. Okay. And we can just do a linear approximation using the changes in x. So the change in x is, well, whatever it is. Change in y is whatever it is. These quantities delta x and delta y. We can use those to estimate this value based on the known value of 4 and using the changes in x and the changes in y. Okay? So you'll need to, the first part just asks you to produce the small increments formula applied to this quantity, delta f, which is the difference in values between f at some base point xy and f at some change point. And then to apply that in the case of the base point. So here the base point is x equals 2, y equals 2. And we know that f evaluated there is 4, so we're interested in approximating this result here. And this approximation to the log of 2, to the natural logarithm of 2, I want you to make use of that as well. Okay? So you can produce the approximation provided by the small increments formula, and out of interest, compare that with a more precise value that you might get from a calculator or Matlab or Sage, something, and see how good the linear approximation is with a more precise value. So that's part A. Parts B and C are about stationary points. Okay, and the rest of after I've done this little introduction to the coursework, I'm going to show you some examples of stationary point calculations. Okay. In part B, you're presented with a function g of xy, and you're told that this has 2 critical points, 2 stationary points. And you're asked to find the location of them, to prove that there are only 2, as the question claims. Find the locations, and prove that there are only 2. Classify them into local maximum, local minimum, or saddle points. And to back up the pen and paper analysis you've done on it with some views of the surface. Okay, so use some appropriate computer package, such as Matlab probably, or Sage, or others, to produce some nice plots of the surface here, where you can see, where you can appreciate the nature of the 2 stationary points. You can see clearly that they are minimums, or they are maximums, or they are saddle points, or whatever they turn out to be. Part C is kind of a negative example. Here we got this function h, and you're asked to prove that it has no stationary points. And finally, in part D, so this is an exercise around the use of Taylor series, or about the calculation of a Taylor series, of a Taylor approximating polynomial. So we're dealing with this function q of xy, which is x squared times y times the tangent of the product xy. And the first thing we might do is, well, we can look up the known single variable Taylor series of the tangent function. Okay, so you can look that up on Google or in a reference book, or work it out from the definition of single variable Taylor series. I don't really care how you obtain it, but use that known Taylor series to do a quick calculation and prove that q, when you evaluate q at h and k, so we're talking about doing the Taylor expansion about the origin here. Normally, as we saw earlier today, we have the base point plus h and the base point plus k. But the fact that both of the base point values are 0 here. So we're doing the Taylors, we're approximating q at a point close to 0. Using the known single variable Taylor series for tangent, we can produce just a quick and dirty calculation to produce this, the polynomial approximation to q. But then in part 2 of that, I want you to verify that this, in fact, is the Taylor approximating polynomial for this function q, up to where you include all terms up to and including order 10. Okay, so we've got an order 5 term here, so you h cubed k squared, that's order 5. And then we've got an order 9 term here, h5 k to the 4th. So this is the formula that we looked at this morning for the 2-variable Taylor series. So what I'd like you to do is calculate this and observe and verify that it is equal to this approximating polynomial that you derived quickly using the single variable Taylor series. But now you won't be able to do it by hand, okay? Because remember, these powers on D are compositions of that number of the operators D, okay? See, this is a fairly complicated function. You've got x squared times y times the tangent of x times y. And if you work out the first order partial derivatives and the second order partial derivatives, even when you get to the second order partial derivative, see, you'll need to have applied the product rule twice and the chain rule for differentiating tan of x times y. So when you get to first order partial derivatives, you can get second order partial derivatives, you can get. When you get to third order and fourth order partial derivatives of this function q, your expressions are taking up the whole width of the page. You probably have to go on to 2 or 3 lines just to fit in the third or fourth order partial derivative. And if you start getting up near the 7th, 8th, 9th order partial derivatives, you'll be filling pages and pages of paper with algebraic expressions, which I do not want you to do. And if you do that, produce pages and pages and pages of algebraic stuff by hand. That's not the point of the exercise. Okay? The point of the exercise is not to do that. The point of the exercise is to make use of Matlab to do the calculations for you. To write a little program, and I'll show you some basic commands. They show you the kind of ingredient commands you'll be using. But to write a little Matlab program, a little script, that Matlab will calculate this for you. Okay? And if you do it right, it'll spit out this value up here. Okay? So it's a little bit of a coding exercise. Okay. And there's already a link, so you'll need to make use of the diff command, which is the symbolic differentiation command. Okay, so Matlab is able to work out derivatives of expressions like this, made up of polynomials and standard functions. It knows what the derivative rules are for those, and it can apply the product rule and the chain rule. And it doesn't mind dealing with long algebraic expressions. It can handle it. It's a computer, it does what it's told, and Okay, so that's a quick introduction to the coursework. Any questions about it at the moment? Do take account of the guidance at the top and on the cover sheet. I mean, you have to explain your work properly. You have to provide rigorous arguments, like in those places like where I wanted you to prove that there's only 2 stationary points to that function. Well, you need a rigorous logical argument to rule out the possibility that there are any other critical points. So your work needs to be well explained. Plenty of explanation in there, not just equations. You know, you need to explain these steps that you're going through. Okay, but if you have queries about this as we go through the next few weeks, feel free to ask, and I'll respond as appropriate. If I get any kind of significant queries from people, you know, I'll email or I'll put the query on Moodle and my answer to it, just so everybody can share in the advice. Okay. So any questions on it? Okay, it's all a bit fresh at the moment, I suppose. Okay, so let's return to here. And now there's a worked example of finding stationary points there in the notes. I'll leave you to read that one and work through that one yourself, but I want to show you a fresh one here, so you just have an additional example. Okay? So this is an example of finding stationary points for a function. So we're going to consider the function g, okay, which has this definition: g of xy is y squared plus y minus 16. So it's this polynomial part multiplied by the sine of x. Okay? And the instruction is to find and classify all of the stationary points of this. Okay, so that's what we're going to do. Now remember, the definition of a stationary point is one where both partial derivatives vanish simultaneously at the point. So we're going to have to set up the simultaneous equations. We're going to have to solve them. Then we're going to find a list of stationary points. And then we're going to have to classify each one using the Hessian Determinant, okay, which was the combination of the second order partial derivatives of g. We need to evaluate that at each of the stationary points. And based on the value of that, we can classify each point as a local minimum, maximum, or saddle point. But before we launch ourselves into that, we can maybe get a peek at the answer or some intuition or good idea of what kind of responses we're going to get if we use the computer to draw a surface plot of this graph. Okay, so just repeat the definition up here if you're still taking it down. So it's y squared plus y minus 16 into the sine of x. Okay, so this is our function g of xy. So if we switch over to Matlab, and the file that I produce here, I'll put it up on Moodle afterwards so you can see the answer. So first of all, we need to define our function g of xy. And we just type in the definition: y squared plus y minus 16. And that's multiplied by the sine of x. Now, is this big enough for everybody to see? Everybody see that? Or should I reduce it? Okay. So we define the function g of xy. We see the output from the definition. Give me a section. Okay, so first now we want to set up the. First we want to plot this and have a look at it. So there are various surface plotting commands in Matlab. One of them is fsurf. An fsurf can take a function of two variables, g of xy. So we've already defined fy. I think if I just run it like that, it will show me over there on the right a nice plot of the surface. Okay. Okay, so we can see a nice shape to the surface. Seems to be going up and down in waves as you go along this axis. Unfortunately, it doesn't label the axes straight away, but If you look at the definition of the function, you can see this factor, the sine x. Okay? Of course, sine, everyone knows is the periodic oscillating sine wave. And that kind of presence seems to be here along this axis. So I think this is the x-axis. So by default, it plots things from -5 to 5 in both axes. But we can ask for a bit more if we say go -15 to 15. And we'll keep it at 5 and -5 and 5 on the y at the moment. So we make it that instead. Okay, so you can see that wave of what looked like maximums and minimums continues, seems to repeat itself along the axis there. Okay, so you can spin the surface around and inspect the surface plot a little bit, but it certainly seems that along this central line, the surface, we've got alternating positives, alternating local maximums and minimums. Yeah. So it looks like there might actually be an infinite number of stationary points. Okay, a row of alternating maximums and minimums. And beside it, if I reduce it down again, just simplify it a bit. On either side of the maximums and minimums, there are what look like saddle points around the maximums and minimums. Okay, this point on the surface here, if you go along one direction back and forwards, you can see this point is acting like a little minimum. In front of and behind it, the surface rises. But if you go the opposite, or if you go in a different direction, you come out of the screen or go back into the screen. So if you come out of the screen, you're falling down the surface. And that's repeated on the other side. If you spin the surface around, you'll see that's repeated on the other side. So this looks like one of those saddle points, okay? Like the midpoint of a horse's back, okay? It's up and down that way, and it's down that way, okay? And if you spin it around, you can kind of see that there are quite a few of those saddle points, quite a few of those around those minimums and maximums. Okay? They seem to be repeated either side. Okay? So just that initial investigation kind of lets us know what we're in for. Okay? We kind of expecting to see an infinite number of stationary points because the presence of this periodic factor in the function. We're seeing minimums and maximums, and alongside them, we're seeing what look like saddle points. So that's always a good thing to do, to investigate the surface plots a little bit to see what's going on with your function. Okay. So we anticipate. Okay. We anticipate an infinite set containing minimums, maximums, and saddles. Okay, so let's go and find it. So the stationary point is, and we defined it today, a simultaneous solution to these two equations, dg dx equal to 0 and dg dy equal to 0. Okay? They are the points x, y, the locations in the domain of the function where both of these equations are simultaneously satisfied, okay? Where both the partial derivatives vanish. So we need to obtain the partial derivatives first of all. So this pair of equations, this is equivalent to dg dx is, what's dg dx? Well, you got this polynomial in y multiplying the function in x. So the derivative is going to be that same polynomial in y multiplying the cosine of x. Okay, that's the x derivative. The y derivative, well, you look at the function in terms of y, it's a polynomial in y multiplied by a function of x. So it's going to be the derivative of this polynomial multiplied by whatever the function of x is. Remember, when you're differentiating This time now with respect to the y variable, you treat the other variable, the x variable, as if it were a constant. So we just see a constant times a polynomial in 1. So its derivative is 2y plus 1 times the sine of x. And this has to be. Okay, so now we know what our equations look like. We're looking for the simultaneous solutions to them. So both equations have to be satisfied. I'll just label these so I can refer to them easily. Now, when you're looking for a simultaneous solution to a pair of equations, we want to approach this very carefully. We want to be sure that we find this, that the points we identify are simultaneous solutions, and we want to be sure that we find them all. So my advice is that you choose the simplest looking equation and fully describe the solutions to that, okay? So equation 2 looks simpler. So equation 2 is true if and only if it's easier to describe the solutions to equation 2. Well, okay, it's a product of these two factors, so if it's going to be 0, it's 0 whenever either of the factors is 0. So when is 2y plus 1 0? Well, that's easy enough. That happens when y is minus a half. And when is sine of x equal to 0? Well, sine of x has lots of zeros. Okay, remember it's it's got an infinite number of zeros. Okay, all these points here. So what are these points? These zeros at the sine graph. They're the points 0, pi, 2 pi, 3 pi, etc. Sorry?
0 here.
The zeros of the function, so the places where the function cuts the x-axis, where the y quantity is equal to 0. Okay. So sine of x is equal to 0 only when x is an integer multiple of pi. Okay. And those are the only circumstances under which equation 2 is satisfied. Agreed? Okay. So that's what I suggest you do. Look at the simpler of the two equations and completely describe the solutions to that. So that means if there are any stationary points, they must satisfy this condition in the round bracket. So either the stationary point has a y coordinate of minus a half, or it has an x coordinate of some integer multiple of pi. But now we also have to have the first equation satisfied as well. So we need to take our description of the solutions of 2 and impose them. Substitute them in, so to speak, into equation 1 and see what extra conditions we get from equation 1. Okay. But now the condition is it can be either of these, either this y value or one of these x values. So let's take the y value first. If y is minus a half, then equation 1 is equivalent to, well, what happens when you put minus a half in there? You just get some value. What you get? You get a quarter. You get a quarter plus minus a half, minus 16. I'm not particularly interested in that value. I just need to be sure that that's non-zero. Okay, so it's some non-zero number multiplied by cosine of x. Yeah? So when is that 0? Because remember, equation 2 will be true if y is minus a half, but we need equation 1 to be true also. So that's equivalent to the cosine of x being 0. And when is cosine of x 0? Well, the graph of cosine is It looks the same, but it's got a phase shift on it, doesn't it? So the zeros of cosine are located at pi over 2, 3 pi over 2, 5 pi over 2, etc. Every odd integer multiple of pi over 2. So a nice way of writing that is every 2n plus 1 times pi over 2, where n is any integer. Okay? An odd integer multiple of pi over 2. Those are the locations of the zeros of the cosine function. So that means we found a bunch of stationary points. Any point with this x-coordinate and y equals minus a half is going to be a stationary point. Okay? So 2n plus 1 times pi over 2 and y equals minus a half for any integer value of n are all stationary points. Are stationary points. So we found one family of stationary points. Okay. But there's another condition to investigate as well. We have to investigate the when x equals n pi condition as well. Okay. So that's only half the story. So the other condition, we go back to get the other condition from equation 2, which was x equal to n times pi. If x is equal to n pi, then equation 1, because remember they both have to be satisfied. If x is n pi, then equation 2 is satisfied. What does equation 1 look like if x is an integer multiple of pi? Well, you're going to have this polynomial bit. And you'll have the cosine of an integer multiple of pi, but that's easy to describe. Cosine of an integer multiple of pi is either plus 1 or minus 1. Depends on the parity and the oddness or evenness of the integer, but it's either plus or minus 1. So it's plus or minus this polynomial equals 0. But that means it doesn't really matter if it's a plus or minus, because the thing is going to be 0 when the polynomial is 0. Plus or minus won't affect whether it's 0 or not. Okay. So under this condition that x is n pi, equation 1 is going to be satisfied at the roots of this polynomial. Okay. So it's a quadratic polynomial. We've been solving these things for years. The solutions there are y is a half of minus 1 plus or minus the square root of 65. Okay? Won't get bogged down in solving the quadratic equation. So that means we found another set of conditions under which both equations are satisfied. When the x-coordinate is one of these, an integer multiple of pi, and when the y-coordinate is one of these two values. Yeah?
I don't understand the second if x equal n pi. What? Can you explain it?
So if x is n pi, I then go back and I look again at equation 1. You see, the x equals n pi was part of the solution of equation 2. If x is n pi, equation 2 is true. But I'm looking for simultaneous solutions. I need both equations to be true. So when x is n pi, I go back and look at equation 1. But you see, it's cosine of n pi. Cosine of an integer multiple of pi is either plus 1 or minus 1. This is where these points here on the cosine graph. Either plus 1 or minus 1. At 0, pi, 2 pi, 3 pi, 4 pi. So it's plus or minus 1 on the cosine factor. I'm substituting x equals n pi, but there's no x there, so it's just the same polynomial in y. And when is this true? Well, it's at the roots of that quadratic. Okay. So you apply the quadratic formula, you get those two values, a plus version and a minus version, two values for the y-coordinate. Yeah. So we found a second set of stationary points. Any point which looks like this, which is an n pi and a half into minus 1 plus or minus square root of 65. These are, all, and it says any integer value n, these are also stationary points. So we found a lot of points. We found 2 infinite families. Okay. Are there any other points? Are there any other stationary points that we might have missed in our analysis? There's one family. Here's the other family. Call this F1, family 1, F2, family 2. There aren't any others, okay? We have to appreciate that what we've got there is a method for discovering these stationary points, but it also proves there aren't any others, okay? Because by definition, stationary points are simultaneous solutions to equations 1 and 2. When we first examined equation 2, we found the complete description of the solutions of equation 2. And we imposed that description on equation 1, and then found the conditions under which equation 1 was true. So we impose the conditions for equation 2 to be true and find out which of those, or what extra conditions you get for equation 1 to be true. So there are no other circumstances under which both equations are true. So it has to be captured by y equals minus a half or x equals n pi, because those are the descriptions for equation 2 to be true. So we should just remark that our method proves that there are no other stationary points. So that's what I mean about being careful and methodical and having a logical argument which proceeds step by step and captures stationary points and captures them all. Okay. There isn't any other stationary point because the stationary point has to satisfy equation 2, so it has to come under one of these 2 descriptions, either y is minus a half or x is n pi. Now this fits with our investigations of the surface. These points here, you see, are a row of stationary points with a changing x coordinate but a fixed y coordinate. These ones down here are really 2 rows. We've got 2 alternatives for the y coordinate and an infinite set of x coordinates. So this first one looks like the central row of minimums and maximums, probably. And these 2 rows, one at this y value, one at the negative version, so side by side y values, and with an infinite set of x values, they look like the rows of saddle points either side of the central minimums and maximums. That's what we suspect, just by comparing with the view of the graph. Well, we can prove that by doing the classification using the Hessian determinant. Okay. So we classify them now. We need to obtain the Hessian determinant. So we use this D, which is this combination of x and y, which is the product of the 2 second-order partial derivatives minus the square of the mixed second-order partial derivative. Okay, so we need these. Will I just produce it in the big long thing? Yeah, that's good. Okay, so d2 dx squared is the minus of the polynomial bit times sine of x. d2g dy squared is a bit simpler, 2 times sine of x. And then it's minus the square of this one, which is 2y plus 1 cosine of x. So that's what the Hessian, sorry, it's a bit small. That's what the Hessian determinant looks like. And we're going to evaluate it at all of these points. Okay, let's try the saddles first of all, or what we suspect are the saddles. So if we look at F2, consider F2. If I evaluate this D at n pi and either of these y points, you could take them separately, but actually you can take them together. See, when you do that, what do you get? Well, see, when you put in n pi for x, the sine of x is going to be 0. So in fact, you don't get anything from these first two terms. Okay? The sine of n pi is 0. So you only get something non-zero from here. Cosine of n pi is plus or minus 1. Okay? And 2y plus 1 just gives you some value here when you substitute that y value in. It isn't 0. Okay? But then whether it's positive or negative is really doesn't matter because we end up squaring it. So really all we need to see is that this is the negative of a square of something non-zero. So that means it's a negative quantity. So this is the only thing that survives. And this looks like a negative of a square of something which is non-zero. So the point is it's less than 0. Okay? I don't particularly care about the precise numerical value. It's just a negative quantity. And so the F2 points are all saddle points. Now, if I was submitting this for coursework, I would evaluate this. I would get the value out of it. But for our purposes now, cosine of n pi is plus or minus 1. 2y plus 1 is something that's got root 65 in it, something non-zero, and we're squaring it and then taking the negative of it. So it's a negative quantity. And the classification scheme that we looked at this morning said if the Hessian determinant comes out as negative, you're looking at saddle points. Okay? So that confirms our suspicions from looking at the plot of the surface. That these two rows of saddle points located at y, at the two y values in these roots, which are just up and down a little bit from each other, separated by half of root 65, which is approximately 3. No, square root of 65 is, that's whatever it is, 8. 8 squared is 64, so 8 divided, so approximately 4, distance of 4 separating the two lines of saddle points. And there's a pair of saddle points at every multiple of pi along the x-coordinate. So that's the family F2. Then we look at our first family that we found, F1. So here we're looking at evaluating D. So what does F1? F1 has an odd multiple pi over 2 and a y value of negative 1/2. Well, you see the y value of negative 1/2 means that this part will be 0, 2y plus 1. That's where the negative halves came from. They came from the zeros of 2y plus 1. So when you put y equals negative 1/2 there, that's all 0. So that bit is all rubbed out. So it's just the product of these two. And you see this is sine squared. So it's minus sine squared times 2 times that polynomial. after we've substituted yes. So this is 65. It comes out as 65 over 2 times the sine value of this quantity here, 2n plus 1 times pi over 2 all squared. So, well, sine, see, this is sine at an odd multiple of pi over 2. These are these points on the sine graph that are up here. These are these maximums and minimums of the sine function. So these are plus or minus 1. So when you square it, you get plus 1. So you just get 65 over 2, which is bigger than 0. That's the point. Bigger than 0. So the classification scheme said that we needed to look at the value of the second order partial derivative evaluated at this point. Okay. So when you evaluate this at this point, so take the same point here, the stationary point, and evaluate it here, you get 65 over 4. Because that's just this, it's just this part here. So you don't have the extra 2. 65 over 4 times the sine of 1/2 of 2n plus 1 pi over 2. Well, that's easy to know. It's 65 over 4 for even multiples of pi over 2. These are these top values of sine. These are even multiples of, odd multiples of pi over 2. No, sorry, 65. Yeah, 65 over 4. So we either get 65 over 4 or minus 65 over 4, depending on whether the sine value comes out as positive or negative. And it comes out as positive for the even values of n. And it comes out as minus for the odd values of n. Because when n is 0, you've just got plus pi over 2, which is sine value is 1. And when n is 1, you've got 3 pi over 2, which is this value here where the sine is negative. So by inspection of the sine coordinate, you get plus or minus 1, depending. Okay? So the point 2n plus 1 pi over 2 and y equals minus 1/2, this point is a local maximum. It's maximum when the second derivative was negative for odd n, and a local minimum. It's a local minimum when the value of d2f dx squared was positive, so that's for even n. So that again agrees with what we saw on the surface plot. Okay? So on the surface plot, we saw this alternating sequence of, because the surface was going up and down. So we had an alternating sequence of a local maximum followed by a local minimum, followed by a local maximum, local minimum, and so on and so on and so on. And that's what we get here. Because when n is 0, that's one of the odd values of n, we get a local minimum. Then you get n equals 1, which is an odd value of n, which gives you a local maximum. Then you get n equals 2, which is, again, an even value, so a local minimum and so on. Okay. So as the various values, integer values of n tick through here, you get the alternating sequence of local minimums and maximums. Okay. So, and all of these classifications, the saddles, and the local minimums and maximums, all of these classifications agree with what we see on the surface plot. Agree with what we see on the surface. Okay, so that example supports your work on the coursework question. It's an example showing you how we can take a relatively complicated function at the start, find its stationary points, at the same time proving that the stationary points we found are all of the stationary points, that there aren't any other ones. So we took a very careful logical analysis to finding the simultaneous solutions, and then classify the stationary points using the Hessian determinant. Okay? And looking at the positive and negative values of it, and the positive and negative values of the second derivative. And all the time, backing it up with what we can experimentally observe about the surfaces. Okay? Okay, just in time, we'll leave it there for this evening.